Okay, so thanks again for joining me, and we're going to do the exercises here that are in today's class. So, in principle, you are able to log in on your session. So I'm here on home, L, LCL, UOT, blah blah blah. So this is always your home, which is here, not mine, of course. And the first thing that we need to do is to get to the questions that we're going to answer today. So we sequenced a mystery bacteria. We want to assemble the genome to know what it is. We will use the SPADES assembler, the St. Petersburg assembler. So first connect to the teach cluster and follow the instructions below. Copy the files mystery1 fastq.gz and mystery2 fastq.gz from home L, LCL, EOT body 25S1004. So that's my home here. Okay, except that I made a mistake here. The entire address should be that. So it should be here. It should be that. That's a bit annoyingly long. And the same here. But you know what I mean. You've done that before. So that's my address here. Oops, sorry. Is this here? So that's here, the path of my address, home, L, LCL, UOT, BioD25, LCOT, BioD25, S1004. And then you have to copy the files that are called mystery1.fastq.gz and mystery2.fastq.gz. So if you look at my home here, you can see that there are these two files, mystery1.fastq.gz and mystery2.fastq.gz. What you have to do is to copy these files to your home in order to get started with work. So you need to do that first. Okay. Copy the file spades.slurm from the same place here. So there's a file which is called spades.slurm. So that's the file here, except that there is something I need to fix with it before you copy it. 410. Okay, so there's this file which is called spades.slurm here in my home. So you copy this as well. And then you have to edit spades.slurm to run the script that assembles the genome of the mystery species. So we've seen this last week. You've done this for the midterm, so you're already quite confident with how to run this. Please work in group if you don't know how to do it, etc. Ask your neighbors. You can, of course, do this. It's no problem. And you will figure out what to do. And then once you've done it, answer the following questions. So which line in the Slurm script speeds up the job by a factor 8? How is this achieved? In contigs.fasta, the contigs are sorted by decreasing length. How big is the largest contig? How big is the smallest contig? Then you have a hint on how to answer that question. How many contigs are there in the assembly? And what is the mystery species? So here you have some help on how to actually answer that question here. So I give you just a couple of minutes to copy the files here, mystery1 and mystery2, and copy the spades.slurm file. I'll just show you in a second how to do it, but in principle, you should remember how to do it. You've done it before. So I'm just giving a couple of minutes for everybody to do that. Okay, so just I'm going to show how, if you haven't done this yet, how you could do it. So you have to do CP, remember that's for copy, and then you have to put this path here, so that's the directory where the file is, and then you enter mystery_1 fastq.gz, and then you have to use the dot here. Okay, the dot means here. So compared to where you are, which is your home in principle, it means that it will make a copy of the file which is in this directory. And we're talking of this file here, mystery1.fastq.gz, and here, which means in your home. You do this, in principle, it's going to work. Then you do the same with mystery2 here. If you like interesting things, you can also do mystery star from the first. It will actually copy both files in principle. Star means complete with whatever starts with mystery, and you have only mystery1 and mystery2. So it's easier to type this way, because otherwise there's always a chance that you make a mistake or type. So that's the way that you can make the copy to your home. Then you make the copy of spades.slurm here, and that's the same command. And like with the place of the file home L lclu_25 lclu_25 s1004, and then the name of the file, and then space and a dot to say copy it here. Okay, so in principle, if this is done, then you can start answering the other question, which is edit space.slurm to run the script that assembles the genome of the mystery species. So when we look at the file, we see that there is this gibberish, which is here. Interestingly, there is no module load in this case, but it says replace X and Y by the files of interest. After completion, inspect file context.fasta and spades_output. So you see there's this command here, which we don't really need to care about. That's not very important here. But it says -o spades output, -1x, -2y. And it says replace X and Y by the files of interest. So not a super hard question. You should be able to figure out what I mean by the files of interest. And after this, you should be able to figure out what to do when you have made the slurm file, how you submit it again. This is something you've done multiple times. So for now, the main question is, what do you have to replace X and Y with, and how you have to do it, if you maybe don't remember how to edit scripts on the cluster. Okay, so the answer is, again, not super complicated. You should use Nano here, which is the editor that allows you to create, not to create, but to modify existing files. Okay, so I'm going to actually make a copy of space.slurm in my case, and to make the original, because I want to keep the original, but I'm going to edit the same way as you would do it. So that's nano space.slurm here. So you have this usual kind of oldish interface for nano, and you gotta go till the X, where you replace here with basically the name of the file that it should be. So that's mystery1.fastq.gz. Then it's a bit annoying. It's too long for the screen, so it does this, but nothing to worry about. And again, mystery_2.fastq.gz. Okay, so if I go, it should look like this. It's a very long line. So -1 mystery1.fastq.gz, -2 mystery2.fastq.gz. Those are the two files that you've copied from my home. And yes?
Sorry, do we have to edit the file path because we're copying the file into our own?
In that, it's a good question. Do we need to copy the file path? No, you do not. Okay, because this here will be run from your home. This here is, as you recognize it, is the path of my home, of the teacher's home, because I have in my home Spades. So you're not installing Spades, you're actually copying it, you're not copying it, you're kind of using it from my home. So that here is me installing Spades version 4.1 yesterday, and you're just going to use my version of Spades. So that's why you need the entire path, but you're not copying it, actually. The rest will be run from your home, which means mystery1 and mystery2 will be looked for in your home, not in my home. And that's why you copied them in your home. So now that we're good to go, we want to exit with Control X here. So I press Control X. It says save modified buffer. Buffer, remember, it's a file. And I say Y for yes. And then immediately it says file name to write space.slurm. Yeah, that's good to go. So I just press return, and that exits nano here. And if I look with a less, for instance, space.slurm, I can see that, yeah, that's good. Now it contains -1 mystery1 fastq.gz, -2 mystery2 fastq.gz. So there's always the chance I make a typo. If I did not make any typo, we're good to go. So how do I submit this again? What's the command? Everybody knows, I see this, sbatch spades.slurm. So if things went well and I did not make a typo, then things should run okay. So we run SQ to see what happens. We see that many people here are running, and there is, for example, someone who's running HTSEC here, which is from another course. You can see LCL, UOT, MMG, etc. So that's someone else using the cluster right now, but we are the accounts at the bottom. Some of us have been running already for almost a minute at the time when I ran this command. So you can see that this is a command that takes a bit of time. What's interesting is you can see here nodes list like 3, 2, etc., but also CPUs 2 and 8. So it's quite interesting to notice that this time it's 8 CPUs. In the previous times we submitted the work, I think it was 2, but I'm not too sure. So we need to wait until this is finished. Of course, I don't know which is my number here, but that should be a number, how much, job 782. So I'm still running, I'm here. So it takes approximately 5 minutes, this one. Okay. So in the meantime, you can already think of the first question. Which line of the Slurm script speeds up the job by a factor 8? How is this achieved? So there was a very strong hint in the last things I said. Yoo-hoo! 1778 has finished, so one person already can continue with the work. I don't know who that is. Lucky you. Well done. Meanwhile, almost everybody else seems to be running. So it was 56, 51 last time I checked. So it seems to stop at around 3:56. So that's about 4 minutes, I suppose, to run the entire script. So while this is finishing, so when this is done, you have to look for the file which is called context.fasta. It's in spades underscore output, and answer the question. Okay, so the contexts are sorted by decreasing length. How big is the largest context? So try to figure out in the output that you see, how could you find the length of the largest context? Also, how can you figure out which is the smallest context? And then there's a hint. Press capital G within the last viewer to go to the end of the file. And also question 4, how many contexts are there in the assembly? Yeah, it's good. We're all finished. The only thing that is running is from this other course there. So if we look at what happened, there is a spades.output that has been created. In my case, it was already there because I ran it yesterday, but now we see there's the new one. So in principle, in spades.output, there is a file of interest, which is context.fasta. So I'll go back to the question so that you can see what you have to do. So I'll leave you with these questions for a few minutes and try to answer them. So how do we answer these questions? So first we can go into spades output. Remember, that's the command cd, change directory, spades output. Then when I do ls, I can see that there's a bunch of stuff, but the ones I care about, the only one I care about is this one, context.fasta. Now to read a file, the easiest is the command less context.fasta, and here we go. Okay, the command, you've done it a lot. It's using less here, less, not ls, and then the name of the file, and you get a FASTA file. So you recognize the FASTA format here with the header, and then you can see all the typical DNA sequences in the FASTA format. So we see here node 1 length 251019, cov 12327292. And I said in the hints that the contexts are ordered by length. So the first context, this one here, is actually the longest. So question for you, what is the length of the longest context? Can anyone guess based on the information we have now? What about it's that here? Okay, like node 1, our biggest context, length 251019. Well, yeah, that's what it is. Okay, so like the longest config is 250 KB. It's quite nice. And that's quite a long piece of config here. And cov 12.32. Let's not worry about this for now. That's the coverage, but we'll get back to it. Okay, so if the first config in the file is the biggest, where do we find the smallest config? Well, it's the last config in the file. We need to go to the very bottom of the file. And there's the hint, which is just press capital G, so Shift G here. And as soon as I do this, bam, I teleport to the end of the file. You see it says end here. And so we see that this one here would be the last config. Okay, it says node 245, length 128, coverage 28. And then we see the sequence here. So what is the length of the smallest config? 128, it's obvious. Okay, there it is. Okay, so that's the way you can just very quickly, by knowing how to use less, you can see how to go from one end to the other. We can also see some weird things here. For example, config 239 looks very suspicious to me. GG, etc. So what's going on here? This is an artifact. This thing is not real. There's nothing in the genome of this species, which is just a bunch of G's here. It's an artifact of this sequencer that they use, which is a known artifact, is that whenever there's no DNA, it sequences G instead. I know that's weird, but when it sequences like a dust or something like this, it thinks it's a G. We don't have time to explain exactly why that is, but if you ever work in genomics, you'll remember, oh yeah, that's the artifact that Dr. Fillon mentioned, the one that produces way too many Gs. Anyway, that's not real. This one is maybe real, maybe not. But anyway, the length is 128. And question 4, how many contigs are there in the assembly? Anyone can guess? 245. Okay, like node 1 to node 245. Each node is a config. So I'm not too sure why they want to call it a node and not a config. I don't know. If anybody looks it up, please share it with me. But there are 245 contigs here. All right, so quite simple questions, these ones. But now the real question is, what is the mystery species? So I'll give you a bit more time to try and fool around with this. You also have a couple of hints here. To retrieve a file to your Mac, the easiest way is to CP it to your home. So first you make a copy to your home, and then close the session on teach, but not the terminal, and type, notice the colon, blah, 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 which is here. This command, which is there. So I'm going to show you how to do this. Why do I show that? It's in case you want to use that file to have it on your computer. This is the way you can retrieve it. So you do cp contigs.fasta to your home. So you can either do it this way with a tilde. Tilde means home, or you can do $home like that. Okay, so that makes a copy of this file to home. When I go home with cd always brings me home, and then I do lr or ls minus l. I should see that now there is a file which is called contigs.fasta. There it is. It wasn't there before. So now it's in my home. Okay. So I got this this file which is in my home, and I would like to copy it to my Mac, to my laptop, the one that I'm using right now. So how do I do this? Well, I create a new terminal here, or I can close the one that I was using before. It's the same. And from here, first of all, I've got to see where am I. So here I'm in my home, which is here. I can go to desktop, for instance, and I'll see that, yeah, indeed, I'm on desktop. So if I copy the file to my computer, to my Mac, it's going to make a copy on desktop if I'm on the desktop. So choose a place where you want the file to be, okay? And then you do scp. So remember there was SSH, and scp, it means secure copy. SSH means secure shell, and scp means secure copy. Then you have to put the your login. So that's LCL UOT BD25 S1004. That's my login. Then the name of the computer. So that's teach signet.utoronto.ca, and then the colon here. Okay, that's the one that I'm giving in the hint. And the name of the file you want to copy. That's contigs.fasta. So it should look like this, and then space dot, because that's the same as copy. Okay, you say copy something from that remote computer, which we don't even know where it is on the planet. Okay, and then use here LCL UOT BD25 S1004. That's my login, and then the usual name of the computer, teach signet.utoronto.ca, colon, and then the name of the file, and then dot here, and then you press enter, and then it asks your password here. Okay, so you enter your password, and if you haven't made a typo neither at this long sequence which is here or in the password, it should make the copy in your computer. If you have a Mac, that's easy. If you have a Windows, that's a bit more annoying. You need to use the secure copy button. So you will have to enter your password. You can then put the file on the desktop with MV contigs fasta on your Mac, or you can directly copy it from the desktop. For mobile extern, you can use the SCP button. So I think there's a button for SCP, and you can look up that particular address here to see how to do this using a mobile extern. I'm not really strong on mobile extern because having a Mac, and I don't even own a Windows computer, so it's hard for me to do anything on Windows. But you can find some help on how to move files using mobile extern. It's somehow easier on a Mac than on a Windows. So then you have the file on your computer. You can open it with whatever you want, even Microsoft Word. It will work, anything you like. So then you can think of ways that you can analyze this file to know which is the species that we were, the mystery species, basically, the one that we were assembling. So here I'm showing that this is my Mac. It's called Iris here, and there is the file contigs.fasta on my Mac. Okay, there it is. I can use less on my Mac, but the interesting thing is that I can move the file around on the desktop. If I do this, it creates the file here. It just appeared. When I do this, I can, double click on it, and then Mac doesn't know how to open FASTA, so that's a bit the issue. But I can still use anything I want, like a text editor, or change the, the end here if I want to do, for example, txt. Yeah, use txt. Now does it know where it is? Oh yeah, that's a text file. Oh, I didn't know. That's so cute. So you have now the file here with a graphical interface. So it becomes easier if you want to, for example, copy things. I can do copy and then paste, etc. So I can maybe think of ways that copy pasting this to somewhere might reveal what the mystery species is. But also the other thing is that on Mac, and I don't know if it's possible on Windows or not, is that I can actually copy directly from here as well. Okay, like if I do Command C here, I'm copying that directly from here, which is kind of useful. So if you, don't manage to make a copy of the file to your home, and you can directly copy the sequence from here, maybe you'll find a way to do something useful to guess what the mysterious species is. So does anybody have a suggestion of what we can do to find what the mystery species is, at least conceptually? Blast. Of course we use blast. We always use blast. That's always the same thing. Okay, so one thing I can do is I can try to be lucky and just, using my trick, I do copy here, and then I'm going to head over to the internet and then say blast, and then just blast it. I'm using nucleotide blast, for instance, and just very brutally copying the sequence here and hoping that I'd be lucky. So I'm using the core nucleotide database, seems fine. So let's go. It's maybe a long shot, but maybe it's gonna work. Oh, well, that was fast. Okay, and we can see that. Oh, wow, look at that. Escherichia coli. And then we have 100% match, and the score is 2,992, so that 3,000 nucleotides that match perfectly with E. coli. So, any guess what the species is? Obviously, that's probably E. coli, right? And that's indeed E. coli. So this is an experiment here, which is a resequencing of E. coli. And we've seen that with the assembly strategy, we can just assemble everything, then use BLAST to find which is the sequence that corresponds to it. It would be more difficult with the reads, okay, because the reads can be too small, they will actually match multiple species, they can have errors, etc. So doing the assembly first allows us to do it nicely. So let's go back. Here I would like to show you something which is quite interesting, is that I can clear the query here, but you see there is also a choose file. So if you want to do it in a way nicely, what you can do is actually take that file and then blast the file. Okay, so that's why I wanted to show you how to do it from your computer. So you can try to find the files. Well, it's called context.txt now, even though that's a FASTA file. So it has now context.txt. I just changed the txt extension so that Mac doesn't wonder what type it is. And if you do that, in principle, it should run. So now, think about it. The query, is longer than the maximum allowed, 1 million bases. You may reduce your query length. I use a standalone BLAST. So what we can do instead is remember the first config is not 1 million base pairs. It's much less than that. So I can just take most of the first config here and then delete everything else. Now we can try that. So it's not necessarily easy to manipulate a text file, but if you have the tools to do it, you can see I'm just keeping just a very large chunk of the first config that is here. I'm saving the file, and so that allows me to blast sequences that are fairly long by doing this. The entire file is too much. It doesn't want to do this. So where is the file? Context.txt it doesn't want anymore. Some weird reason. Okay, and so when you do this time it should work. It doesn't complain anymore. So that allows me to have really large sequences that I can blast in one go. So what you will have to do for the last part of the midterm, my recommendation is, yes, use files. Don't copy paste small fragments, because you will get into trouble if you don't align the entire sequence of what you have assembled here. Well, we can see that this is still E. coli, of course, but now we have aligned 17,000 nucleotides. That's much more, and that gives us much more confidence that this is actually that strain of E. coli, not another strain which is there, as you can see. Okay, like this one, for example, over these 17,213, we have a higher hit for that substrain compared to the others. So this is here the strategy that you can use in order to answer those questions for the third part of the midterm. Are there any questions, things you'd like me to show again or that you did not follow with this demonstration? Okay, no, then I'm stopping the recording here.